Okay, so it's great to see everyone, and thanks for coming. So just let me know if you can hear me okay, and if everything's good. We can start. So let's get the slideshow. Okay, I think that's fine. Excellent. Right, so what I'm going to talk about today is a little bit about hardware and how we can actually think about building brains. So this is something that a lot of people in the transhumanist and the singularity communities are always talking about, which is this idea of uploading or substrate independent minds or simulation, or numerous other terms for this phenomenon, but I'm sure everyone knows what I'm talking about here. So here I've just put a picture of a brain on this slide to try and frame the rest of this talk. So I just want everyone to kind of look at the brain for a while, because this is really what people are aspiring to build when they talk about building thinking machines. So the idea is to try and capture the computational power of this very object in a different substrate. So if you just look at this, it's kind of very different from what we normally think about when we consider the phrase computers. So there have been a lot of focus on scanning brains, trying to get the information out of the human brain so that we can process it on our computer systems, and so that we can reconstruct a model of the brain in another substrate, which is usually silicon. And there are many, many people working on in this area, using techniques such as fMRI, EEG, MEG, and more recently SEM imaging, so actually taking slices of brain tissue and looking at the underlying structure and the connections in order to try and build a good model. But I'd like to ask a slightly separate question, which is how substrate independent can a mind actually be? And how well can we emulate a whole brain in another format? So even if we had all the information about the structure, the neuronal activity, and all this kind of thing, does the hardware actually matter? So does the substrate we're putting the mind into matter as much as the model that we're actually trying to put in there? So I'm going to argue in this talk that it does, and that we should spend a lot of time thinking about two things in particular that might be problematic with this desire to create machine intelligences or virtual versions of ourselves in software. So the first thing that we need to consider is that the algorithms that we're running on these pieces of hardware, and the second is that we need to consider the pieces of hardware themselves and how the algorithms tie into those pieces of hardware. So I hope in this talk that people see that these two questions are kind of the same, sort of two sides of the same coin. Okay, so what methods have people been trying to use so far to reconstruct intelligences in machines? So you can split the approaches taken so far into two distinct categories. So the bottom-up approach tries to use a reductionist set of methods to try and figure out what the most important unit cell or the lowest level building block that can actually encode or embody the idea of intelligence. And it might be the case that you need to put lots and lots of those building blocks together before you actually get anything that looks like intelligence. It might only be an emergent property of very, very many of these building blocks. And this is the idea that people use when they build biologically inspired neural networks, such as those designed around the idea of the perceptron quite a few decades ago. And so there are kind of mathematical models of neurons or building blocks that you can start with, and in themselves they're not particularly interesting, and it's only when you connect them together in very large quantities that you start to get interesting behavior. And the models of them can be different, and they can have different amounts of power to them. So a standard neuron model is the perceptron, which just turns its output on or off depending on what the inputs are that it's receiving. And then there are slightly different models of neurons, such as the Izhikevich model, which actually uses a kind of nonlinear element. So it captures the behavior of the neuron in a more mathematical model, in a much more compact way. So you can see that there are different models of neurons that actually encode some computational activity in different degrees of software complexity. And so on this slide, I've put a picture of a visual from the Blue Brain project. So the Blue Brain project actually takes this idea of using building blocks to the extreme. So instead of simulating individual neurons, it actually attempts to model the structure of the components at a much finer level than that. So it looks at the behavior of individual ions and collections of ions within the neurons themselves. So this is a very, very fine scale program. And the result is that it's quite an impressive program, which it's able to react realistically to the introduction of agents on the similar scale. So things like molecules and drugs. So you could simulate the effect of adding molecular agents to this brain simulation. Unfortunately, the downside of doing it this way is that the overall scale of this simulation you can achieve is very, very small. So the Blue Brain project currently only simulates a few tens of thousands of neurons, and actually trying to scale this up to an entire brain, or something we might even consider to be exhibiting intelligence in any way, is actually a really daunting task. And this simulation, this model of the brain, is already consuming tens of kilowatts of power to run the supercomputers that this thing is actually working on. And the simulation itself also runs very slowly, so you might need to put in hours or days of computer time just to simulate a few milliseconds of brain activity. So what we see here is that the Blue Brain is an exceedingly faithful representation of an underlying system that can be intelligent. But in practice, when we try and build something in this way, the combination of this particular algorithm, of these building blocks, these neurons, running on this particular hardware configuration, which is these IBM supercomputers, is just really inefficient. And I hope you can kind of see that, because a Blue Brain simulation consuming tens of kilowatts of power compared to a similar thing it's trying to simulate, which is a tiny volume of brain tissue which is consuming microwatts. It's kind of inefficient. So there is another approach to building intelligences, which is known as the top-down approach. And so I also put on this slide a picture of Kismet, which was an artificial intelligence project which was undertaken at MIT in the late 90s. And Kismet is a robot. And the idea is to try and capture some of the essence of human-like intelligence in a machine. But the idea is very, very different to the Blue Brain project. And the reason why is that Kismet was designed with what's known as a top-down approach. So what Kismet was trying to capture was the highest level functional features of behavior. So it's the broadest possible description of what the system might be doing. And then the idea is to try and capture the behavior in an algorithm, rather than trying to start with small building blocks and see an emergent behavior from them. So these two examples are really interesting to compare, because they're both attempting to get intelligences into other substrates. And they also both run on conventional, what we'd call conventional silicon processors. So they both use standard computing tools, although probably Blue Brain's processors are much, much more powerful nowadays than Kismet's were back then. And so another similarity is that these two things are, in some respects, trying to run a same algorithm, which is updating weights in neural networks to try and capture the way that a system learns. So, but you can see that these two things are very, very different. and one of them is actually the problem with the Kismet approach is that the problem is under constrained, which means that there's not enough things you can change in the algorithm to try and capture all the subtle complexity of a thinking system. Whereas in Blue Brain, the problem is that the model is over constrained, which means you can change all these parameters of tiny molecules and structure in your cortical column, but you have no idea what changing any of these things might do. So the question is, what can we do and where should we pitch ourselves on this sliding scale between these two extremes when we're trying to actually create thinking machines, and how does the hardware tie into this thing? Because in both these cases, people didn't really think about it too much. They were like, well, we'll just get the biggest supercomputers possible to run this model, and then, you know, everything else will be fine. So I would argue that we actually need to think about the way we're implementing these thinking programs, because it's obvious from these examples that certain algorithms run more efficiently on different types of hardware. And this is a really fundamental problem that we can't avoid. So if you think about your desktop PC, it has different modules for dealing with graphics, and it has multiple cores now, so that when you have to do highly parallel tasks, the processor is able to cope with that. And some systems even have maths coprocessors for doing specific operations, such as matrix inversions or whatever you might want to do at the time. So the idea is that there are particular algorithms which are written into all our computers, which interact with the hardware on a very low level. And so I think that we really need to think about this idea when we're trying to capture this in thinking system. So here's my first kind of controversial statement of the presentation, which is that computational power can only help you if the algorithm that you're trying to implement scales. So this is what worries me a little bit when people state this argument of Kurzweil's, which is that in year X we'll have enough computational power to simulate the brain. The problem is we don't really know what algorithm the human brain is running yet, so I'm not quite convinced by this argument, because it might turn out that if the algorithm we need to run on these systems does not run efficiently, then it might be okay to run simulations of tens of neurons, or hundreds, or thousands, or millions. But if something scales exponentially, then at some point there'll be a sudden jumping, but there'll be a point where it just becomes completely intractable, and it might be at the millions level, or it might be at the billions level. So I think even though Moore's law is increasing compute power at an exponential rate, what we should realize is that these problems that we're trying to solve on these computers might also be increasing in difficulty at an exponential rate, and then you just get a fight between two things that are increasing exponentially, and we would have no idea whether or not which would win, really. So there's another argument in favor of thinking about this a bit more, which is that even if you agree with Kurzweil and you say that these exponentially increasing computer resources will mean that we'll be able to simulate the human brain within 20 years. The question is, if our algorithm is not running efficiently on the hardware, then we can just throw more and more computational power at it. But the downside to that, we'll be wasting 99.5% of all that computing power on the inefficient part. So you can imagine that all these millions of connected supercomputers that might be required to do a simulation, well, most of them are spending that computing power generating heat, and there's only maybe 0.5% of the power is actually spent doing your simulation. So I think if we spend a little bit of time thinking about how we can make these things more efficient, then I think we can be sure that we'll get there at some point in the future, even if we have these problems. So let's start thinking about the thinking systems that we know about in order to work out how we might make some of these models or these algorithms more efficiently embedded into hardware. So if you think about standard semiconductor processors, they're mostly two-dimensional. So some of them have actually many layers inside the processor, but in effect they're many layers which are kind of flat sheets, and then they're just connected in certain places. So they're a little bit more than two-dimensional, but then they're certainly nowhere near three-dimensional. And the reason for that is that there's a limit to the amount of connectivity you can get between layers in a semiconductor device. And also there's a fundamental limit. If you try and make something three-dimensional and it's generating a lot of heat, it's really hard to get the heat out of the center of the processor object if it's inefficient. So we can already see that we have a problem with these things being inefficient and generating heat, and then we want to try and make them better connected to better simulate the brain. We kind of run into a problem there. So biologically, if we look at systems such as collections of neurons, we find that they're actually formed from many different types of connections. Some areas are highly two-dimensional, some areas are highly three-dimensional. And the other thing about biological systems, which we don't seem to have quite yet captured in our model, is their ability to change themselves over time. So the ability to actually change something structurally and change its connectivity as part of the fundamental algorithm that you're trying to capture in your hardware is actually really important. And it's something that's not captured very well at the moment by semiconductor chips. So we need to think about these problems. So if things are three-dimensional and they're changing their structure over time, does this mean that the hardware we're trying to simulate these things on also needs to have these properties? We just don't know this, and people kind of avoid this question because they say that the exponential increase of processing power will eventually be able to solve all these problems and you'll just be able to get around it. But I'm not sure that this is the case, or it's something we should at least think about. So even before we go into the algorithmic side of these neural network circuits, just looking at the structure of them and the way that they are biologically able to change suggests that there might be some difficulties in how we can actually recreate this in software. So we excuse me, we have to find some ways around this problem. We have to be a bit more clever about it. So most researchers today believe that the brain, and so not just the brain but other intelligent systems as well, work using what's called a hierarchical method of learning, or a hierarchical model. And so this is what this diagram on the slide is supposed to represent. And this is what's known in research as a deep neural network. So one thing to note about this diagram, it's very schematic, but it has a very structural component to it. So, oh, hang on 1 minute. I just need to plug my laptop in, sorry. Sorry about that. It was about to die. Okay, so yeah, so the idea of this deep neural network is that it's a very structural thing, and if we want to try and build this type of learning architecture in hardware, then might we need hardware that's also has a lot of structure to it. So I should really explain what this thing is actually representing. If you imagine the lowest level, so the little dots that are the lowest ones in this hierarchy, these are supposed to be representing the data coming in from our sensory data streams. So for example, things like vision, audio, touch, taste, and smell. And the amount of raw data that's coming in through these channels into our brain is quite huge. And what people believe the brain is actually trying to do with all this data is find some way to compress it so that it can actually then work with the compressed data and process the compressed data, so it doesn't actually have to process the underlying raw input data. So instead of working with the data at the very lowest level as it's coming in from the senses, that might be like individual phonemes in speech, or which is coming through small cells vibrating in the inner ear, or maybe it could be signals coming from light sensitive cells in the retina. What the brain does is it tries to cluster together pieces of this information and make generalizations from it, and then it processes those clusters. So you can see how if it clusters together lots of objects to make a higher level node, like in this diagram, there are fewer of them to have to deal with. So it can kind of make generalizations and then process the generalizations rather than having to get stuck on the underlying details. And then you can imagine it forming even higher level nodes which correspond to clusters of these clusters. So these are much higher level, much more abstract ideas like emotion, like the feeling of pain, and like a lot of our social interactions dealt with at this level. So why does it do this? The reason is because it's faster, and the brain is actually sacrificing precision for speed. So if the brain can learn a few rules of thumb or a few abstractions and then work with those, rather than having to work on the very lowest level of input data all the time, then it can actually run a lot faster and it's a lot more efficient. And one thing I just wanted to mention was it seems obvious that the brain is doing this when you see things like optical illusions. So if you think about it really hard, you can see what the optical illusion is really underneath. So you can see that the two lines aren't parallel, or that there are you switch between two ways of seeing a 3D object. But these things do fool the brain, and the reason they do that is because they're actually being processed on a generalized level where you're not really seeing the detailed input data at the low level. So this approach is also known as deep learning, and it's a very powerful way of processing information about the world in real time. And so the other thing it allows us to do is, if we have an incomplete data set, it allows us to predict parts of data that are missing. And this is something that conventional algorithms don't do very well. So unless you have all the input data, you can't generate the output because there's something specific that gets you from A to B. Whereas with one of these deep approaches, because you're processing a generalization, the system can then fill in the details underneath because it has a more powerful model of the way the data is working. So I just had an anecdote, a kind of fun idea about this. So if you imagine a human watching TV, and you imagine a thinking machine watching TV that didn't have one of these kind of deep learning structures behind its intelligence. So when we watch TV, we're able to use this hierarchy of abstract concepts to know that the person on the TV is real, and that they exist somewhere else, and that they're not actually trapped inside our television. But in order to actually know that about the world, we have to have some very high-level abstract concepts that we understand outside of just the visual information that's coming in to us from the TV. So a system that didn't have any of this framework would think that, okay, pixels are changing color on the television, and they look like a human, so maybe there's a human inside the television, or something like that. So if we're fairly confident that this deep learning idea is a good algorithm to capture the essence of intelligence and our ability to learn, then do we actually see processes that have the ability to embed this kind of structure very efficiently? And the answer is no. This kind of thing is very difficult to model on processors nowadays, and the reason why is if you look at the diagram again, all those low-level nodes have links that go up to the next level, and they're all working in parallel. And the processors we have nowadays are not very good at doing things in parallel. So some of them have quite a few cores, but we're talking about millions or billions of connections here, and we just don't have anything like that at the moment. So these technologies are actually slowly being realized. So for example, graphics processors have been graphics operations, as the name suggests. But it's actually noticed that some of these processors are actually good at other things, like pattern recognition and learning, even though they haven't been designed to do that specifically. So what's happened here is that people noticed that graphics processors were just a little bit better equipped to run learning algorithms than general purpose serial processors with small numbers of cores. So they started using them for that. But just imagine how much more efficient systems could be if we actually designed them around the very way we think that learning algorithms work in the first place. So we're not just picking something off the shelf because it's a little bit like what we want. We're actually designing things to be exactly what we want. And there are actually some good pointers along that this might be happening. So there are new benchmarks that are being developed. Very recently there was one announced called Graph 500. So most people buy supercomputers and high-end processors based on their benchmarks. But the problem is they're still benchmarking for these very serial arithmetic operations that we're used to thinking about computers as doing. They're not being benchmarked for things like these massively parallel learning tasks, which is what we want processors to be good at if we want to use them to build intelligent machines. So hopefully some of these new benchmarks that are coming forwards will actually help sort out this problem, because people will see these things as being useful to have in their processors. Okay, so to kind of summarize so far, not all problems are born equal. And so what we need to do is design hardware which actually captures the essence of the problem we're trying to solve, rather than just throwing the general purpose computing power at things and hoping that the problems will scale, because and it's not clear that these problems do scale in a way that's kind to us. So I'm hoping in the future there'll actually be a wealth of new processor specialization where the hardware is actually designed with a specific application in mind. So this is the idea behind something called co-design, which I wrote a blog article about recently, if anyone's interested in reading that. It's on my blog. So one of the technologies that I'm working on to try and combat these problems and address these issues is using quantum algorithms and quantum hardware as a new way of designing processors. So the question is, can quantum processing help us? And the first thing I'm going to say is that when I'm discussing quantum processors and talking about intelligence in the same light, I don't want people to think I'm talking about quantum effects in the brain necessarily. So I'm talking more of a top-down approach, like from the from the slide with I'm more on the Kismet side of things than the blue brain side of things, and for that reason I'm not talking about the very low-level structure of the brain. And so some people believe that there are quantum effects which are fundamental to the computational power of the brain. I'm not actually convinced by this argument myself, and I think we can have large models of intelligent systems without needing any quantum mechanics whatsoever. However, it is useful to realize that quantum effects give us new computational resources, and we can actually use those to help us perform computing operations more quickly and more efficiently. So it doesn't necessarily have to be a direct link between quantum mechanics and the brain for us to be able to use quantum mechanics to make our computations better. So let's see. Okay, so I'm not going to go into the details of how people believe the brain works currently. But the main point is that if we're trying to emulate it, we need to take our best guess at the algorithm we think it's running so far, and then try and match our hardware design to the algorithm. So on the right here is actually a picture of it's actually a photograph of one of the chips that we're working with at the moment. And the idea of these chips is that they don't work anything like standard CMOS circuits where you have zeros and one binary states, and then you do arithmetic operations on them, such as addition or multiplication. So the processors just don't work anything like that. What they're actually trying to do is something that's much more suited to this deep neural network hierarchy of learning. So on the left here, I've got a picture of a way in which a neural net is commonly depicted. And what the chip is actually trying to do is it's trying to learn the weights in that network, and the weights are those links that go between the nodes. And so if you remember, I was saying that the problem with processors nowadays is that they're not parallel enough to change or sample all these weights at the same time. But the processors that we build have this parallelism built into them intrinsically. So the one thing they're designed to do in the world is solve the problem of finding those weights in a neural network. So they might be totally awful at addition or multiplication, but they're really, really good at discovering those weights. And the idea here is that you have to build a completely different hardware configuration for something to be good at doing that problem. And the thing about this is that a lot of problems in learning can actually be tied back to problems that these processors are designed to solve, which are called optimization problems. And so I'll only talk for like a minute or so about how these things work. But if you imagine that learning or training one of these networks involves discovering a useful output when you start changing the inputs. So the problem is that all the inputs interact with one another. So when you change one, you have no idea what's going to happen to the output. So the way that these chips work is that they're actually able to put all the inputs into a quantum superposition, so they can effectively try everything at once, and they can learn the weights in the neural network by, if you imagine the processor is doing, say, thousands or millions of tiny experiments all at once by changing all these input states and seeing how it affects the output. So although this hardware is kind of unusual and unconventional, it actually captures the essence of this problem really well. So it's kind of a promising approach. And the thing is, there might be even better hardware to tackle this problem that just hasn't, and better algorithms that haven't been discovered yet. So this is what I mean by the best guess. It's like, let's take the way we believe things to work currently and make hardware that really captures that. And then if we discover we're slightly wrong later, we can build some new hardware that captures the new model. But we should always be considering this at every stage. We can't just build a tool and throw it at every problem. So I think that the ability of systems to exhibit intelligence might be currently bottlenecked by our hardware. And that's quite a strong statement, but I think that it will become more and more true in the future. So I think that even if now we're not being bottlenecked by the hardware, we will be eventually. So we can simulate tens or thousands of neurons fairly easily, but when we try and do billions or more than billions, if we're interested in super intelligence, then this is going to become a problem at some point. So I think that, like, the one thing I wanted to say about this, and it's kind of a little bit sad and depressing really, is that the problem at the moment is that people are not building these new hardware technologies. And you might ask the question, well, why not, if they're so promising for these approaches? And the reason is that building hardware is exceedingly expensive. And when people look at what to spend their money on, they're looking at what will be good in maybe 6 months' time or a year's time to get some money back in return. So people don't invest in things because they're cool and they might be useful in 20 years' time. It's not how things work. So the problem we're having is not an engineering one with these new architectures. It's actually a socioeconomic, and it's a political one. It's like, do people really want these things to be developed now? And the problem we've got into with silicon technology is that it's so well established that there's a really high barrier to entry for any other type of technology other than CMOS circuits. So although these technologies are really, really promising, they need a lot of time, money, and effort invested in them to get them up to that level that silicon technology is currently held at. And unless we get them to that level, we'll never be able to take them beyond that and really solve some of these problems very, very efficiently. So what will happen is maybe in 15 or 20 years' time, maybe even sooner, we'll run into this sudden problem of, oh, we just can't do this anymore with these processors. It's intractable. It just doesn't scale. And then the problem then is that we won't have put any effort into the other technologies that could have solved this problem for us. So that's kind of my little cynical rant about why we actually need to invest in different and disruptive technologies now, because they could help us with problems later. And I noticed some people are talking about ASICs in the text chat, and that's actually, it's a similar problem. So ASICs tend to be designed to solve one very specific problem. So it's kind of similar. We need to be designing new styles of ASIC to really solve these problems. So I think this is my conclusion slide, which is a bit odd because it does need some explanation. But the basic idea here is that with general purpose computing, I feel that we're kind of getting stuck in a sort of Stone Age. So if you think about people in the Stone Age, they use their stone tools to solve every single problem that they build weapons, build houses, to open nuts and fruit and things. And so I'm kind of like, at the moment, I'm likening the computer industry to the Stone Age. We're using similar processes to solve every problem. And what I think we need to do is kind of stop relying so much on that method, and we need to reinvent the Bronze Age. So I think when bronze came along, it was much better at certain tasks than stone, but yeah, it was initially hard to find and work with if you're used to working with stone. So, but it was really useful for certain things. So I think that we need to move away from the Stone Age of general purpose processing into the Bronze Age or Iron Age of these new tools. You can never fully replace stone with bronze; it's too expensive. But having this in our kind of computational arsenal could really embellish the way that they're solving problems at the moment. So what worries me is that there are these vast resources in front of us, but our ability to actually engineer them for future gain might not happen. So I think that we need to really think about how to build these new tools and give them at least a little bit of credit to take us from the Stone Age into the new age of solving problems efficiently and impressively. And I think any advanced civilization would be proud of us if we did that, rather than wasting all our computing power on generating heat. So the slide here is actually showing one of the chips that we built to do quantum processing. So, and that's the end of the talk. I want everyone to just remember that the substrate is a key part in all of these things, especially when we talk about substrate independent minds. So thank you very much for listening. Any questions?
I have a question, an observation. Yes, we were discussing about ASICs in the text chat, and I still think that there is a very basic difference between software and ASIC, and this difference is that to start writing some software, at least at the demonstrator level, is within what an individual can afford. And in fact, there have been so many examples of very smart software written by a single person without spending money. Well, of course, you do have to spend money after that to industrialize the demonstrator. But as far as software is concerned, even a person or a small group can begin. Whereas when you move to hardware, things are still extremely expensive, even if you stay at demonstrator and prototype level. So that what I was thinking is that we have this thing now that you keep hearing about, open manufacturing and personal fabbing and all that. Do you think of any possibility that this trend could evolve into a personal capability to make application-specific chips?
Okay, I think it's an interesting question, and about ASICs in general. I think having maybe ASICs are in an interesting case because they're also designed to solve a very particular problem. But this idea of having personalized processors, which so Giulio, do you mean things that kind of we're able to reprogram, like FPGAs that can then be reprogrammed into solving any problem?
No, because that is a capability that we already have. In terms that, I mean, it doesn't cost that much money to buy some baseline FPGA hardware and to program them oneself. This is still very far from the possible efficiency of a chip which is made explicitly for that application. So yes, FPGAs are a very useful step in between software and application-specific hardware. But we do have that capability already. I'm wondering whether we will get the capability to manufacture our own application-specific hardware exactly like we write our own software now.
I see. Okay.
In an affordable way, of course.
Yeah. I think that's an interesting question.
Because what has really made the things evolve so fast in the field of software over the last couple of decades has been that at some point the world of software has started to harness the wisdom of the crowds, and by having millions and millions and hundreds of millions of people writing software and collaborating with each other, at the end you do get some very efficient software because of an evolutionary process that should happen in the hardware field as well to realize your vision, I believe.
Yeah. I mean, one thing that you could imagine is if we had some kind of hardware and software joint development framework. So this would, because it's very expensive to make hardware, what you could do initially is simulate that hardware in some conventional computer. But what you'd be showing is that if we did build this as a separate entity, it would be much more efficient and much faster. So, you kind of be like running your emulation of your new piece of hardware on conventional computer, but using this idea you were saying, Julia, about crowdsourcing things. If we had something that allowed people to program the hardware and the software simultaneously, and then that item could then be a potential candidate for a new program. I think that would be a very powerful method, but I don't know how many people would do that, because another problem is that programming, like hardware and software, are very separate nowadays in the way that people work, and there's a good reason for that, and that is because in the past we have wanted to abstract away what the hardware is doing, so that people can write software independently of that and it can run on any platform. But I think for specific problems like these deep learning frameworks, I think that we do start to see this problem coming through where the hardware actually matters. So if people care about those kind of problems, they should be designing things based on keeping in mind the hardware as well as the software that we're writing. We find this a little bit because if you look at these GPU based chips are becoming popular now, and this GPU framework. So people are actually now programming in things like CUDA, which is NVIDIA's GPU framework or platform for developers. And this is really cool because what it means is that developers are kind of thinking about the hardware that they might want to run their programs on, not just thinking about the programs anymore. So I think things like that are quite promising. We need more of that.
Okay, let's see who has more comments and questions in the chat. Hyunsuk, just say it, just speak or type.
Oh, Hyunsuk's question is already there somewhere. I can't find it.
I had found it, but I need to hold the cursor still when I go over it. One moment, I know how to do that, right? What if the substrate and the algorithms are so closely entangled that they are not distinguishable, like in the brain?
Okay, yeah. Yeah, so that's a good question, and I think we don't know the answer to that question yet. So it might be that there are efficient hardware platforms we can represent that structure in efficiently. But I think that, I guess the main point I was trying to get across is exactly what Hyunsuk's saying, which is that the algorithm in the brain is inherently tied in with its structure, and so when people are thinking about reconstructing the brain in software, this idea is like thrown out. I don't know if you can actually abstract the structural component away from the hardware, or whether we'll actually have to build hardware. So this comes back to this idea of the ASIM versus AGI. And one thing you could think about is, can we just modify the brain so that it has properties that we want and doesn't have the unwanted properties? So most people agree that the brains are quite a good place to start from, if only we could somehow make it less so it doesn't degrade over time. It's not sensitive to disease or damage. And we could copy it. So if you imagine if we could do all those things with the brain, we wouldn't really need all these like computer processing techniques people are using at the moment. So the best emulator of the brain is the brain itself. So one thing you could think about, which is kind of extreme, but is if you just imagine building something, say using molecular manufacturing that was exactly like a brain, but it was made of some other material, for example. And so the question is this actually possible? And I think the answer is yes, but it depends to what degree you're trying to capture how the brain works. So it really comes back to this algorithmic level of are you trying to make something that just is a little bit like a human, or are you trying to make something that's very, that you don't mind being very different? I don't know if that actually answered the question at all, but I think I was just rambling on about brains for a while. I don't know what you want me to say about carbon vapor deposition. In what context? Okay, so so I guess I could say something about other technologies in general. So obviously I'm slightly biased towards the technologies and the systems I'm working on at the moment, but there's a good reason for that, and it's when you try and build anything, then the further away it is from something that exists now, the harder it is to get it built on a large scale. And usually the reason for that is because it's expensive and you need a lot of research and development effort to go into a new technology. So the reason that we're interested in, say, superconducting processors is that we can take a lot of the techniques from the field of semiconductor processing and apply those to the way we build chips. So building chips is actually really, really difficult. So when people say, actually, this ties back to something that someone mentioned in the text chat a few minutes ago, which was memristors. And so this is something that irritated me recently. Is I read a story about memristors on the internet, and the article was saying that some researchers working on memristors had suggested that in the future they might be used as a next generation technology for DRAM, and that I can kind of understand how that might be the case because, you know, they're very efficient as memory storage devices. But then this article went on to say how because they're a more accurate, a potentially more accurate way of modeling neurons, that we'll be able to build brain-like processors entirely of memristors very soon. And things like this just I find really, really bad because building a processor out of anything is really, really hard. You don't just like throw together a bunch of memristors and then you get a processor. You have to design all the control circuitry to go around that. You have to find a way of talking to the processor. You have to look at the heat generation and the efficiency of the thing, and you actually have to build this in a way that doesn't cost you the earth to do. So you have to build it in a kind of using economies of scale in a pre-existing foundry, because like setting up your own foundry is going to cost you $1 billion. So when people say like we've discovered a new technology, like I don't know, it could be nanotube single electron transistors, or it could be memristors, or it could be I don't know, like molecular quantum computing or something. It's like this leap that people make from we've discovered a new component, and then we're going to build like a brain in silicon or in in some other substrate straight from that. It's really, really dangerous to say things like that, because it takes many years to actually build processes. So sorry, I'm ranting again. Anyway, yeah, I think it was an IEEE article. But I think, so to come back to William's point, I think everything is possible. So things like from the field of nanotechnology, there are lots of potential candidates, but it's like there's no magic technology we're just going to discover and then it will revolutionize everything within a year. All these technologies needs at least 20 years of hard engineering work and people to fund them in a way that it gives us a framework to be able to develop them towards commercial products. That will need that amount of time and effort. Yeah, thanks, Natasha. So you could pick any technology you like. It could be your favorite technology. Say it's like nanotechnology or something. It's like you still need a roadmap to get from the promise of that technology to something that's commercially deployable, and that's the hard bit. It's not making the scientific breakthrough in the first place is not difficult because scientists are allowed to explore. But when you start trying to commercially engineer products, you're not allowed to explore anymore. You have to have a plan and a roadmap of how to get from the thing you find promising to something that people want to buy. And that's really the difficult bit. What if any parts of human physiology would be crucial for building substrate-independent minds, for transferring, copying human brain or mind? Well, I think that this is kind of going into a different area, but I think that you'll need to mostly simulate everything. So I personally am a fan of what's known as embodied cognition, which is the idea that if you're trying to build a thing that's similar to a human or an animal or a kind of any organism, you need to simulate or emulate that organism and its interaction with the environment. So I don't think that there'll ever be this idea of kind of like brains in jars with some way of interfacing with them that doesn't capture all the subtleties of human interaction with the environment. So things like the moving of limbs, just the feeling that we have when we're hungry. If you imagine the things that humans think about most of the time on different cognitive levels, it's not abstract mathematical and scientific problems, which are the things we seem to want to put into these human-like intelligences. It's things like regulating our breathing and our body temperature. It's things like, are we hungry or thirsty? I mean, I'm always thinking about that. It's things like, are we cold? And this is like what we spend 99% of our processing power on. It's not really doing the things that we think we're doing. So I think that that Natasha, you're right. We need to really consider the role of the human body and the human in the environment when we're trying to build biologically inspired networks. So more questions. Let's see. So is it possible we cannot duplicate the complexity of the brain in another substrate? Yes, it's possible. I think that again, it's a question of scale. It's how close you're trying to get to the original. So when you say duplicate, I don't think you can ever duplicate anything, because by definition the most efficient simulator or emulator of the human brain is itself. So if you want to copy a brain, then it has to be that same structure. And I'm not really a great fan of the Church-Turing thesis, because I think it works well in theory, but it doesn't work in practice, because in practice you have a lot of real-world restrictions for things like, I mean, it's in the very nature of the title of that is got the idea of the Turing machine in it. And the Turing machine, one has to remember, okay, it's a very computationally powerful system, but it's also intractable to build a Turing machine. You can't actually build one because it requires an infinite amount of resources. So it's like anytime people talk about being able to take the algorithm that the brain is running and move it onto another substrate because this is what Turing machines do, then, well, I'll say to them, but you can't build a Turing machine. It's always some approximation to a Turing machine. What you find in practice is that those approximations make all the difference. So I think that it's entirely possible. I mean, by definition, we can't duplicate the complexity of the brain in another substrate. We might be able to capture some parts of it that we consider to be important. But yes, that question is it does have philosophical implications, but they're also tied in with practical problems, which is kind of, I like philosophical problems get hardcore and get like dirty in the lab. That's the kind of science I like doing. So I don't know if I may have missed some questions because they kind of went up fast. So if anyone's got any more questions. I didn't say when it gets dirty in the lab. Okay, you can check the audio feed. I'm going to be quoted now and...
Suzanne, I'm afraid, as a matter of fact, you did.
Did I? But I did say it as part of a longer sentence.
Right, but you know, a scientist should be used to being misquoted.
Yes,
okay.
This is true.
So let's check if there is any more questions. I don't think so, as a matter of fact. Yoon-Suk has more of a comment. You read that, Susan?
Okay, AI and machine learning are too focused on... Is that solving... My text chat's gone out. Okay, solving problem. Okay, yeah, real autonomy is coming up with problems. Yeah. I think that this is a good reason why ASIM is important, because I think taking the bio-inspired side of things is a really good place to start. And I think that if you abstract too much and you get too much into the algorithmic side of things, then you lose focus of what you're actually trying to do in the first place. So yeah, so I agree. I think you just need input from all the different areas, really. And actually, it's the same with when you're building things. If you look at the theory of machine learning, and then you actually try and build systems to implement some of those ideas, you again hit a lot of these problems.
Okay, I think there is no more questions which hasn't been answered yet, and some people have to leave. We should really thank Suzanne for a great talk. Thank you very much for coming. Thank you, Suzanne, and see you soon.
Yep, see you soon.